Should be. We're gonna start. We're not waiting.
So basically, fossils tell us that organisms of the past were very different from those that are alive today, obviously. And the changes that have taken place within life on Earth are shown through macroevolution. And macroevolution is the pattern of evolution over large periods of time. And evolutionary change above the species level, including the origin of new groups of organisms or a shift in the broad pattern of evolutionary change over a long period of time. That's basically the full definition. And specific examples of macroevolutionary change can be seen in the origin of key biochemical processes like photosynthesis and the emergence of the first terrestrial vertebrates and the long-term impact of mass extinction on the diversity of life. And changes like this basically help us understand the evolutionary history of the Earth and everything that's taken place over, like from the creation of the Earth until now. And so our focus is the hypothesis of the origin of life and the fossil record and what it tells us about the major events of history in life, and specifically the factors that have helped shape the rise and fall of different groups of organisms over the time of the Earth. All right. So, conditions on early Earth made the origin of life possible. The earliest evidence of life on Earth comes from fossils that date of microorganisms that date back to about 3.5 billion years ago, and observations and experiments in chemistry, geology, and physics have led scientists to propose a hypothesis concerning the origin of life, and they think that the chemical and physical processes on early Earth, with the help of the emerging force of natural selection, could have produced simple cells through the sequence of 4 main stages. And the first is abiotic, which are non-living cells. The synthesis of these small organic molecules such as amino acids and nucleotides. The joining of these small molecules into macromolecules, which include like proteins and nucleic acids. The packaging of these molecules into protobionts, which are droplets with membranes that maintains an internal chemistry different from their surroundings. And lastly, the origin of self-replicating molecules eventually made inheritance possible. So, and all of these predictions lead to experiments that can be tested in the laboratory, and then we'll talk about those later. So, the Earth and other planets of the solar system formed about 4.6 billion years ago, and they formed from a condensed vast cloud of dust and rocks. And for the first few 100 million years, life most likely couldn't have originated or survived on Earth at all, and this is because the planet was still being showered with like rocks and ice from the original formation of the solar system. And the collisions that happened in the formation of the solar system generated enough heat to vaporize the available water and prevent seas from forming, which ultimately prevented like life because we need water and stuff like that. And this most likely occurred about 3.9 billion years ago. And the conditions on early Earth were obviously very different from what they are now. And the atmosphere is guessed to be like a thick vapor with various compounds that are said to have been released from like volcanic eruptions. So basically the atmosphere would contain elements such as nitrogen, carbon dioxide, methane, ammonia, hydrogen, and hydrogen sulfide. And as the Earth began to cool, the water vapor condensed into oceans, and much of this hydrogen escaped into space. And so then we go on to the Oparin-Haldane hypothesis. And basically what happened in 1920, a Russian chemist and a British scientist hypothesized that the early atmosphere of the Earth was reducing, which means it was electron adding, and they believed that in this environment, organic compounds could have formed simple molecules. So basically they thought that the energy for this organic synthesis of molecules could have come from lightning or intense UV radiation. And Haldane suggested that the early oceans were the solution for organic molecules from which all life arose. And then after that, in 1953, Stanley Miller and Harold Urey of the University of Chicago tested the previous theory and created an environment that they thought could be similar to the environment of early Earth. And they compared these in their experiment in a laboratory, and their apparatus created a variety of amino acids found in organisms today, as well as a variety of other organic molecules. Okay, any questions? Because I know I went really fast.
Yeah.
Sorry. Abiotic synthesis of macromolecules. The presence of small organic molecules like amino acids could not have been enough to cause the emergence of life as we have it today. And every cell has a vast assortment of macromolecules, including enzymes and other proteins, and nucleic acids that are all, that's spelled wrong, nucleic acids that are all essential for life as we know it today. And researchers have been able to produce amino acids and polymers by dripping solutions of amino acids onto like hot rocks and sand or clay. And the polymers, when they do this, the polymers form spontaneously without the help of enzymes or ribosomes. But